optimized Genesis sequence.
Right. I must say, it's quite an experience getting to speak in a cinema. It makes me think of all the good times I've had in the cinema. For example, watching my favorite movies of all time, which are, of course, the Lord of the Rings trilogy. I still remember the first time that I went to see The Fellowship, and I became an instant, lifelong fan. Now, The Lord of the Rings is not the only trilogy that I am a big fan of. This is also true for the HTTP protocol, of which the third installment was standardized about 2 years ago. Now, you might think, Robin, that is a bit weird. How can someone be a fan of a protocol, you big nerd? Well, I have an excuse, okay? I actually did my PhD research on protocols and their performance, and I actually got to contribute to the design of HTTP3. My name is actually in the RFC somewhere. So I do have some reason to be here and talk to you about these node protocols and what they are doing. And I think that's important because they do start, I wouldn't say a revolution, but the next step in the evolution of the internet. They changed quite a bit. Not so much the top layers of the protocol stack though, right? If you see on top what I've called the HTTP semantics, that's things you all know and use. Things like get and post and head, or the status codes or headers. Those are things that of course stay the same across all the HTTP versions. What has changed over time is how those things are communicated on the network, right? Especially from HTTP1 to HTTP2, that was a huge, huge step, completely different ways. But from HTTP2 to HTTP3, actually, if you look at it, nothing much has really changed. In terms of features, in terms of concepts, they're very much the same protocol. In fact, for a long time, HTTP3 was called HTTP2 over QUIC. And that's because the real revolution here, the real innovation, is one layer below that, at the transport layer, with the new QUIC protocol. QUIC is intended to kind of replace TCP, the transport control protocol, which runs most of the stuff that we do daily, over the coming decades. It is not something super new, something that we've never seen before. In fact, it looks a lot like TCP in many different ways. It's connection-oriented, it has things like congestion control, in such a way that many people often call QUIC TCP 2.0. But there are enough differences, key differences, that warrant it naming it its own new thing. For example, it deeply integrates with TLS, the Transport Layer Security Protocol, which encrypts the data. In TCP, that is a completely different thing on top. In QUIC, it is fully integrated into the protocol. The other thing we're going to look at is that QUIC is running on top of UDP, which is very weird, and we'll see soon why. Now, one thing you might be wondering at this point is why? What is wrong with TCP? Why do we even need a TCP 2.0 or even a QUIC? The thing is, TCP still works, but it's showing its age, right? It's several decades old, and there are some inefficiencies in the protocol that are starting to become a hindrance. One good example of that is the TCP handshake. Right? If you want to send up a TCP connection, you first need to do the orange lines here, the TCP SYN-SYNAC handshake, to set up the connection. This takes one round trip on the network. Then, depending on the TLS version, you need either 2 or 1 round trips to set up the encryption, and only then can you start sending your HTTP level requests and get responses. Right? And especially if your client and your server are far away, several tens to hundreds of milliseconds, this starts to add up. Right? This starts to become some overhead that we want to prevent. This is one of the reasons that companies like my employer, Akamai, exist, content delivery networks. We put the edge servers as close as possible to the end user so that the delays on the network here are as short as possible. Now you might think, Robin, that's easy. Okay, I can solve that. I can imagine how to do that. We can just combine the TCP and the TLS handshakes in the same round trip, and then we save a full round trip. And that's actually a good suggestion. I don't blame you for that. But you might be surprised to know that this has already been around since 2011. This is something called TCP Fast Open. And yet, even today, in 2024, this is barely deployed on the wide internet. Why is that? Well, it's because we're all sitting on a throne of lies. Okay, lies that we tell ourselves about how the internet works. If you've ever had a class on these things, you might have heard something like, TCP is an end-to-end protocol. It only deals with the client and the server, and it doesn't care about how the data comes from one point to the other. That's for the lower layers. That's for IP to handle, right? TCP is only client and server. Conceptually, yes. In practice, however, there are plenty of things in the network, which we often call middle boxes, that do look at TCP level data and even TLS level data there as well. These are things like load balancers and, of course, firewalls that need this to implement their features. So let's imagine you are a firewall, okay, who hasn't been updated to know about this TCP fast open thing. So what you expect is a normal TCP handshake, which is basically just an empty SYN packet. That's how TCP starts. That's what you expect. What you actually see on the wire is a filled SYN packet with extra data. Now we know that extra data is actually the TCP fast open extension and that TLS handshake data. The firewall does not. The firewall sees random garbled data, which could be valid, or it could be an attacker trying to smuggle some data past its defenses. So the firewall, of course, has no choice but to be very conservative. It has to drop this unknown packet because it could be an attack. So what happened in practice when we tried to enable TCP fast open on the wider internet, over 80% of all connections started failing. Because firewalls just drop the SYN packet and nothing ever happens, right? So that's the big problem that we have with TCP today. It's not that we don't know how to change it or make it better, it's that we can no longer practically evolve it in practice. Because if you want to change something, you don't just need to change the client and the server, you also need to change all these middle boxes in between to make it practically deployable. And TCP fast open is just one example. There have been many over the years that have taken years to even decades to find some kind of foothold on the actual internet, right? And it's not just TCP either. TLS actually had this problem as well. So TLS 1.2 was for a very long time the final version, or the most recent version. When they tried to start deploying TLS 1.3 on the wider internet, a lot of security appliances just dropped it, right? Because they didn't know about the new version. The solution they had to come up with was to disguise TLS 1.3 as 1.2 on the wire. It pretends like it's 1.2, and then you simply have a new extension there on the bottom, supported versions, that tells, I'm actually 1.3, you know? And weirdly enough, this actually worked. Enough middle boxes were fooled by this simple trick to make TLS 1.3 deployable. A very funny anecdote about that is that QUIC also uses TLS 1.3, and only 1.3, but it uses it as a full protocol. So even QUIC pretends it's using TLS 1.2 on the wire, even though it can't even do that, right? Now I notice none of you are laughing, okay, but I promise you, to us protocol nerds, this is peak comedy, okay? This is hilarious. So this is a solution that TLS could do, kind of a nasty workaround, but it works. We couldn't do that for TCP. Wouldn't work. So what QUIC does is take a very radical approach. It chooses to now encrypt most of the transport level packet as well. So on TCP, if you use TLS, you're basically only encrypting the HTTP stuff, right? Which is good. Those are your credit cards and your passwords. Nice. But everything else, the packet numbers, acknowledgements in the TCP packet header, those are plain text on the network. Anyone can see those. Anyone can change those, right? And that's where the problem happens. And so that is why QUIC deeply integrates with TLS. They now encrypt most of the transport level packet header as well. Things like packet numbers are no longer visible on the wire to things like firewalls. So this is QUIC's solution or attempt to make sure that itself can remain evolvable over the next 30 years of the internet. The idea being that if we ever want to make a new version of QUIC or change how the QUIC protocol works, we now do indeed only need to update the clients and the servers, because all the middle boxes in between can't read the packet headers in the first place because they're encrypted. And so they won't break if we try to deploy something at scale. That's the main reason. This extra encryption gives us a little bit extra security, a little bit extra privacy, sure, but that's not the main reason we're doing this. The main reason is to make sure we can change stuff in there and that stuff won't break on the internet. And it's for the same reason that we run this on top of UDP. Some people still say, oh, QUIC runs on top of UDP because it's faster. That makes no sense at all, because everything that makes UDP faster than TCP is undone by QUIC, because QUIC re-implements everything that makes TCP slower again, like handshakes. The only reason we're running this on UDP is to make it practically deployable on the internet. Again, if you try to make a third real transport protocol next to TCP and UDP, a lot of routers, a lot of firewalls will simply balk at that. They're trained to only expect TCP or UDP, so the only practical way to do this is run it on top of UDP. And then we finally get to HTTP3, right? Ideally, we would really just run HTTP2 on top of QUIC. And for a long time we tried. That was actually a large part of my PhD, was trying to get that done. In practice, there were just enough changes between QUIC and TCP that we couldn't just take HTTP2 one-on-one and run it over. So we had to make a few changes, just enough to warrant naming it something else. In my opinion, still mostly for marketing reasons. And that's how we got HTTP3. Now you can think, Robin, that sounds like a lot of work just to save one round trip on the network, right? And it's true, because QUIC default handshake now does exactly what the TCP fast open tried to do, right? It combines the transport and the TLS handshake into one round trip. Of course, that's not the only thing it does, right? There is a ton of additional both security and performance features. I basically like to think that we took everything we learned in the past 30 years from TCP and some new stuff, bundled it together into one nice little package, and that is now QUIC. And hopefully we can keep evolving that in the next 30 years. Now, one of the caveats of this is that you don't necessarily get this full package all the time. A lot of times you're going to have to choose between either security or performance. You're going to have to make conscious trade-offs. And I've prepared 3 examples of this. A trilogy, if you may, where we're going to look at these things. And the first trade-off that I'm going to explain has to do with something called the zero RTT handshake. So as I just said, QUIC's main handshake is the one on the left, already better than what TCP can do. But in practice, QUIC has an even faster option, which is zero RTT, zero RTTs of overhead, because we can now send the HTTP request and get a response in the very first round trip, the fastest you can possibly get. Now you might ask, why would you not just do that all the time? Why do you need the left one at all if you can do the right one? The problem is, if you've never seen the server before, you wouldn't have encryption keys to encrypt that first HTTP request on the right, because those encryption keys are communicated in the black arrows. So you would have to send that first request unencrypted. That's of course no longer done. We don't want to send anything unencrypted on the internet. So the way we do this is actually kind of a clever way. We use the first column as a bootstrapping connection. So the very first time you go to a server that you don't know about yet, you're going to do the normal, longer handshake. Once you have that encrypted channel there, you can then exchange encryption keys for the next handshake after that, right? And so from the second connection onward, you can actually use zero RTT and encrypt your first HTTP request with those, what we call pre-shared keys, right? So that works. This is how we can do zero RTT in a safe way. Again, a bit of a nasty way of bootstrapping, but it works. But there are other security problems with this as well. For that, we first need to understand why we even need this transport level handshake, right? Why do we need the SYN ACK and then especially the third ACK there as well? From the client perspective, this is easy. It's to determine if the server is actually online and willing to speak to this client. But why does the server need to get that ACK back? For actually pretty much the same reasons. It's to check if the client is willing to communicate to the server. And this is weird, right? Obviously the client wants to communicate to the server. It sent the SYN packet. What are you talking about, Robin? Well, something you might not know about is an attack which uses something called IP spoofing. An attacker can send a packet from their own computer, from their own network, but pretend it's coming from a different IP, their victim IP, right? So in this case, the SYN-ACK from the server would be sent to the victim. The victim, of course, has no idea what this means because it didn't send the SYN. They just drop the SYN-ACK on the floor and the connection stalls out. This is exactly what is supposed to happen. This is why the connection handshake is needed. Because if you don't do this, for example, the DNS protocol, which is based on UDP, which doesn't do a connection setup, you get something like this. The DNS query gets sent, and the server immediately replies with the response towards whatever IP it got from the request. And so if you use IP spoofing, in this case, for every 1 packet the attacker is sending, the DNS server sends 5 packets back to the victim IP. So if you're setting up a DDoS attack where you want to overwhelm the victim with a huge amount of traffic, you basically amplify the attacker's traffic, hence amplification attack, by 5 times, just by bouncing, reflecting it off of a DNS server. Now 5 times sounds bad, actually is quite manageable on today's internet, but there have been cases of bugs, for example the mem crashed bug a couple of years ago, that had up to 51,000 times amplification, and that of course gets out of hand really quick, right? So this is something we need to protect against in QUIC as well. Because of course, like we said, the transport level handshake protects against this. QUIC, sure, it has a transport level handshake, but with 0RTT, that handshake hasn't been completed yet, right? We're trying to be so fast, already sending stuff, we haven't verified that the client actually started the connection before sending information. So on QUIC, if you would do a 0RTT request, much like a DNS query, if the server would just start sending this potentially very large file towards the victim, you would get this amplification attack as well. Of course, the people who made QUIC were aware of this, and they said, we will have a limit of 3 times amplification vector. So whatever the client sends to the server, we can only send about 3 times as much before we have to stop and wait for the client to send us something back so we can verify this is an actual client and not someone whose IP is being spoofed. So this is how we can do 0RTT encrypted and also kind of mitigate that it can be used as an amplification attack. That's not enough though. There are more attacks. One of the main ones is called a replay attack. Because 0RTT, the request is fully encrypted, sure. The attacker can't read it, they can't change anything about it. They can, however, make copies and send those copies to the server as well. So if you have any type of request that changes permanent state, the typical example here is if you do a bank transfer, you transfer money in the 0RTT request, that might be executed multiple times. I think that's a stupid example. I don't think that's realistic at all. But really, any type of permanent state change from a request, even something as incrementing a counter, could be gamified by an attacker by replaying 0RTT requests. This is why you will see that some deployments, like those of Cloudflare and Fastly, limit which type of requests you can send in that 0RTT. To, for example, only GET requests without query parameters, because they are unlikely to trigger a permanent state change in a database somewhere, right? Now I could keep going, because this is really just the entrance to the dragon's den that is 0RTT security. Okay, there is so much more to this, but I think that the general concept is clear, right? You have this very simple thing you want to do. You just want to shave off 1 round trip on the network, but that suddenly requires you to take into account a huge amount of potential security risks that you have to deal with, and so the complexity of the protocol goes up and up and up. That's one example. The second part of our trilogy is very similar, which talks about a completely new feature, really. This is something that TCP does not have, which is something called connection migration. To understand that, I want you to imagine that you are a hobbit. You're sitting in your cozy hobbit hole, you've just prepared a nice dinner, and you have your cell phone connected to your Wi-Fi because you want to watch a Netflix movie while you eat, right? So you're getting ready to take the first bite until suddenly there is a knock at the door. Who, oh who, could be this disturber of the peace? It is, of course, the wizard Gandalf, who has come to invite you on his quest. Right? Now, on one end, you really would just prefer to stay home, right? Enjoy the dinner, watch the movie. On the other end, you have a severe case of FOMO, right? Fear of missing out. Otherwise, you wouldn't have been at Devox in the first place. Okay? So you're thinking like, yeah, maybe I should go with Gandalf on his quest. And so you grab all your things, you run out the door and you yell, I'm going on an adventure. Okay? Now imagine what happens to your internet connection when you do this. You were connected to the Wi-Fi, right? But as you run out of Hobbiton, you of course go out of range of the Wi-Fi access point as well, and you lose the connection. Now luckily, smartphones also have cellular uplinks, right? 4G, 5G, so you automatically switch to the new type of internet. And you might be surprised to notice, but 5G coverage in Middle Earth is actually pretty good. Okay? Thanks to the Palantir Corporation, they've been building these big cellular towers all over the place, so it actually works quite well there. That's not the problem. Okay? The problem is this transition period. And you've all had this, right? When you go from your Wi-Fi to the cellular, there is always like a couple of seconds to a minute where the internet is flaky. And especially if you're doing like video conferencing or something active, you will see this, right? The image gets hazy, it gets low quality, it starts stuttering, that kind of stuff. The internet connection is of a bad quality until it fully switches. And it's this moment, going from one network to the other, that we're going to want to improve with this new connection migration feature. Right? Now first let's understand why this happens. Why do we have this degradation in quality? It is because a TCP connection isn't a real physical thing, right? It's not an actual cable somewhere. It's just a concept of these two IP addresses, client and server, and two TCP ports. Combined, we call this the 4-tuple. That uniquely identifies the TCP connection. If you change just one of these, in this case, the client IP address, the TCP connection becomes unusable because the server has no way of knowing that this new 4-tuple is actually the same as the old one. So all the existing TCP connections have to be torn down, and completely new ones have to be set up, which again takes some handshake time and stuff to get going, and that's why you have this interruption of service. So QUIC wants to prevent this, wants to keep the same connection live, even though you cross network boundaries, with a very simple concept. It's called a connection ID. We just assign a number to each individual connection, and when you change networks, sure, the IP might change, but the number stays the same. And so the server knows, this is actually still just the same connection. I don't need a new handshake. I can just keep using this one. Okay? The way that works is also quite simple. The connection ID is just put into the new QUIC packet header for each and every packet. It indicates which connection it belongs to. It's actually one of the very few unencrypted parts of the QUIC packet header. This works very well, elegantly, but it breaks one important thing, which is a stateless load balancer. So load balancer, you could do this in many ways. You could actually keep a database on the load balancer of which client goes to which backend server, but that requires a lot of memory. So especially large-scale setups use a stateless load balancer, where they basically just take a hash of, again, that 4-tuple, because it never changed in TCP, right? A hash, a stable hash, and then you just use an algorithm to map a hash to one of the backend servers. Works very well until you start changing those IPs. Now, of course, very simple fix. You just need to update your load balancer to use the connection ID instead, because that does remain stable, and so you can use that to decide your routing. That's the basic idea. That's not how it actually works in QUIC. Because if you would deploy it exactly like this, you would have a lot of nation states very happy with you. Because this makes for a perfect geographical tracking vector. You're basically assigning a unique number to an individual user that stays the same no matter which network they visit in their country, right? Terrible, terrible, terrible idea for privacy. And of course, not something that is actually in the protocol. The way we prevent this is inspired, of course, by the Lord of the Rings, right? Lord of the Rings, you don't want the ring to be found by Sauron, so what you do, you change ring bearers halfway through the movie. The same thing goes with QUIC. You start off using one connection ID. Once that connection has been set up, client and server are going to exchange additional connection IDs that they agree map to the same underlying connection. So here they say that the green square and the purple circle are actually the same connection, even though they're different numbers. So that when the client changes networks, it just switches to this next connection ID as well. The server knows about this, so it can just keep using the connection. The attacker or the tracker cannot, because the new connection IDs are negotiated in the encrypted connection, which of course they don't have access to. Works very nicely, completely breaks stateless load balancing. Right? Because now we don't even have the stable connection ID anymore, because now this changes as well. It took a long time to find a proper solution for this, until finally someone said, you know, what actually is this connection ID? It really is just a random number, an integer, right? In practice, it's between 4 and 20 bytes. How about we just take the first part, let's say 2 to 3 bytes of that, and encode the number of the backend server that we want this to go to. Just put it in the connection ID. Right? Just a small part, and then the rest of the connection ID can stay random. So that if you have other connections going to that same backend server, of course, they will share the first couple of bytes. Everything else is still random, and we still have our random connection IDs for unique connections. Very clever idea, super hacky, but it works. You see, I keep repeating this a lot. That's how protocols are made, people. Now, this works. However, the question then becomes, who chooses this connection ID? Because for the start of the connection, it's the client that initiates the connection. The client has no idea about your backend setup. They don't know how many backend servers you have or whatever. They can't encode that backend number in there either. So what the real solution is, and I promise this is the final one, this is what's actually happening in QUIC, is that they split the connection ID into 2 different sets. Kind of like how the fellowship was split, right? Sam and Frodo go to Mordor, the rest goes to Rohan, or dies. Spoiler alert. So basically you have one set of connection IDs for the client, in this case the yellow and the cyan. The client starts with this yellow. It doesn't know yet what the server wants, so it just keeps that as a random value. And then the server says, well, my connection ID with that backend number encoded into it is the green square. Send it back. And from then on, they both know each other's connection IDs, and everything kind of works. So that's what actually happens. Now, I could keep going. Just as before, this is not the end. We haven't talked about how to firewall this. We haven't talked about how DDoS interacts with this, and so on. It's so much worse than you could possibly imagine. But, again, the message, I hope, is clear. You want to do something relatively simple. You want to improve performance during a handover between one network and the other. But to do that in a secure way, you pay the price. In this case, in terms of protocol implementation complexity. Right? So by the end of this whole process, you might not notice this is actually the same Hobbit that we saw at the beginning. Right? At the end of the movies, he looks like this. So I think this is kind of the message that Lord of the Rings tried to tell us, you know. Do not follow your dreams, because you will end up looking like that. Right? Same thing goes for protocols. Don't implement them, because that's how you end up. So I've now talked about 2 different things that have a performance benefit, but a security trade-off. So let's finally talk about something that has mostly the performance benefit and very little security trade-off, which is QUIC's removal of what is called the head-of-line blocking problem. To understand that, we again have to go back to, of course, Lord of the Rings, where you have all these different races in Middle-earth that are of different heights, right? You have the hobbits that are very small, you have the very tall elves, and anything in between. Now, all of these actors are, of course, normal human-sized. So they had to find various different ways of trying to make them look different heights. So for example, sometimes, in this picture, the hobbits are actually just sitting on their knees to pretend to be smaller than the humans. In other times, The humans and the elves might wear these kinds of stilts, specifically designed stilts, to make them appear taller than the lower folk. They also, of course, use a lot of green screen, but one of my favorite techniques is that they also used body doubles. So stand-in actors that are actually much smaller or taller than others. So in this picture, for example, here on the left, this is the actual normal actor. This is Billy Boyd playing the Hobbit. But on the right, that is not Sir Ian McKellen. This is actually a cameo by famous American basketball player Shaquille O'Neal, right? One of the tallest people in the world. Now, this idea between this problem between large and small, tall and small, is something we have in HTTP as well, with the head of line blocking problem. To understand that, we need to first kind of understand how stuff is actually sent at the TCP level as well. So let's say here we have a JavaScript file. HTTP adds headers in front of that. And then, if you put this into TCP packets, it's usually going to get split across multiple different TCP packets, especially if you have a larger file. That's one file. If you then have a second file, for in this case the CSS file, it kind of looks like that, where a part of that CSS response might be in the second TCP packet, and then the rest is in the third one. Now with this setup, this is how HTTP 1.1 works. How would you know where one is finished and the other begins? That's purely based on that content length header. So in the beginning it says content length 1,000. That means the next 1,000 bytes after the headers are all going to be the JavaScript. And only after that can you start looking for new headers, in this case for the CSS file, which have their own content length as well. Now because of the way that this is set up, you get the head of line blocking problem. For example, if your JavaScript file is very large. So let's say here we have several megabytes of JavaScript and only 10 kilobytes of CSS. We have to wait for that full JavaScript to be downloaded before we can send the CSS. The JavaScript at the head of the line is blocking the CSS behind it. And this is bad because you can imagine that it would be more efficient to do something like this, right? Either send the smaller file first or chunk them up, send the chunks in a multiplexed way so that the smaller file is downloaded first, gets to be parsed and maybe compiled by the browser much earlier than normal. It's not just large files either. You can imagine also having two REST API calls, for example, where one takes a long time to complete because it needs to do a lot of database lookups, for example. It would be more efficient to first reply for the first one and then wait for the second one to complete. Right? So that's the head of line blocking problem. And it can't really be solved in HTTP 1. Let's take, for example, the middle one here, the multiplexing. This doesn't actually work. You can make this nice diagram. It wouldn't actually work in practice because there is no way to tell HTTP 1, my JavaScript actually doesn't run for the full 1,000 bytes. It only runs for, let's say, 300 bytes, and then something else is going to start. There's simply no mechanism in there to be able to do that. That's one of the main reasons they invented HTTP 2, to get around this issue. And the main way they do this is quite simple. They now do have like the concept of extra headers. It's called frames. These are called data frames. These are actually appended before the normal HTTP headers that do indicate I am now going to send you smaller chunks instead of the whole resource at the same time. So in this case, the data frame says I have a stream with ID 1. We know this is a CSS file here. And I'm sending 450 bytes of this first stream. It doesn't have to be the full file, just the first part. Now HTTP 2 knows after these 450 bytes, I need to check for another data frame header to know what else is coming here. And we can now say, oh, actually switch to stream 2 now, which is my JavaScript. Send a little bit of that, and so on. So this is how you can get this multiplexing or chunking going on at the protocol level. This is how HTTP 2 solves the HTTP head of line blocking problem. You can now easily send other resources before things, even if the JavaScript here was requested first. However, it doesn't solve this problem completely because there is a similar problem at the TCP level. Again, TCP was not created with the idea of multiple different resources at the same time. TCP thinks it's just sending one file at once. It sends one byte stream, and every TCP packet carries a certain offset of that byte stream. That's how TCP works. So even though at the HTTP2 level, we now know we actually have 2 streams, 2 files, TCP doesn't know anything about that because it hasn't been updated. So what happens now if there's a packet loss? The second packet gets dropped on the network. It needs to be retransmitted, right? We know, the HTTP2 level knows, that actually the CSS file is complete. There is no loss in the CSS file. It's only the JavaScript file that has suffered a loss. So conceptually, you could already give the full CSS data to the browser to execute, only waiting for the JavaScript. Conceptually, you can't because TCP doesn't know anything about that. TCP thinks this is one file, I have a gap in my one file, so I need to wait until that gap is filled by a retransmission before I can send up the rest. So even though data in packet 3, 4, 5, and other things might have arrived, they are stuck in the TCP level buffer until this one packet is retransmitted. So again, we have head-of-line blocking, this time from a lost packet, blocking everything behind it, even though it has arrived. So this is one of the things that QUIC then finally solves. HTTP2 solved HTTP1 head-of-line blocking. QUIC solves TCP head-of-line blocking. They both do it in very similar ways. What we basically just did was take those concepts from HTTP2, the chunking, the different streams, and we just put them into QUIC in the transport level as well. So QUIC has something very similar. It's not called data frames, it's called stream frames. But the concept is exactly the same. You just say, QUIC, I have multiple streams, and here are the chunks of these streams that I am sending. This makes HTTP3 a little bit easier, right? We don't need to deal with all the chunking and stuff at that level. We can just reuse QUIC's chunking below that. Why does this solve this problem? Well, imagine again, this packet gets lost. TCP doesn't know anything, but QUIC does. QUIC doesn't know we're sending CSS and JavaScript. No, but it does know we have 2 independent streams, stream 1 and stream 2. And even though I have a packet loss, stream 1, I have bytes 0 to 449, and I have bytes 450 to the end of the file. So there is no gap for the stream 1. I can just take all of that data, give it to the browser for processing. The only thing I need to block is stream 2, because there I don't have the first 300 bytes. Right? So that increases efficiency even in the case of packet loss or packets that are delayed. QUIC can basically knows that there are independent things going on and treat them all individually, all the way up to what the browser or the client wants to do with the resources. This then finally is also the main reason why we couldn't just run HTTP2 directly over QUIC. Because they're basically trying to do the same thing. Right? They're both trying to do this chunking at the same time. And we really tried, but it just turns out that the implementation of getting this correct is just way too complex. It's way easier to just drop all of that from the HTTP level and just do what is on this slide instead. That's one of the main reasons we have HTTP3 and not H2 over QUIC. Now, I've been talking for a very long time on very technical topics on a Thursday morning. I'm sure everybody is tired. So let me switch to something else, a bit lighter topic that I'm sure everybody would find much more interesting, which is, of course, women with beards. Now, you might remember this in the second movie. The dwarf Gimli says, "It's true that you don't see many dwarf women." And Aragorn replies, "Well, it's because of the beards," indicating that there are a lot of masculine women in dwarven society. And there is an extended scene in the third movie where they're having a party and the dwarf is drunk. And at a certain point he says this, he says, "It's the dwarves that go swimming with little hairy women." Now, I think this is the best line ever written for TV or movies ever, right? And if you don't agree with me, I don't think we can be friends, okay? It's that simple. This is genius, okay? Now, this concept of the masculine woman also appears in the main storyline with the princess Eowyn, right? She desperately wants to go to war to help defend her country, but she can't because she's a woman, right? And in the country of Rohan, only the men can fight. So what she ends up doing is disguising herself as a male soldier, rides into battle, and she ends up defeating one of the main antagonists of the story, the Witch King. Right? Talk about girl power. Very satisfying character arc. The final thing that I absolutely love is an anecdote about how all of this was made. Again, these riders of Rohan, they often have these huge battle scenes, right? These are thousands of horses thundering down on the orcs. According to the story, all of these are men. Only men are allowed to fight. Now, they were filming this in New Zealand, and they wanted to get as many real people, real horses in the shot so they didn't have to do everything with CGI. So they basically asked for volunteers. Anyone who's in the area from New Zealand, come to us, bring your horse, we'll dress you up, and you can be in the battle scene. Now, due to various reasons, most of the people that showed up were women. So in all of these cool battle scenes, where canonically these are all men fighting, actually, most of these are women with fake beards and mustaches. I love these movies to death, okay? Now, this whole concept of replacing something inferior, the men, with something superior, the women, is something that, of course, we're also doing with HTTP, right? We're going from 2 to 3, making things better. The final question you might have after all of this is, how much does this actually give me, right? Show me the numbers, Robin. How much performance benefit do I get from all of this? Well, a company called Wix, I like to call them the GeoCities of the 2020s. You know, they have millions of websites, and they actually did test this a couple of years ago. They found remarkable results. They found that HTTP3 is up to 50% faster for time to first byte, so the handshake setup that we talked about before, 50% faster than HTTP2 in a lot of the geographies. Amazing results. Now this is where it can hurt you to have an academic in your team, people. Because when I saw these results, I got very skeptical. Right? Let's look back at the theory that we introduced in the beginning. HTTP2 should be 3 round trips, right? The TCP, then TLS 1.3, and then the HTTP request, 3. On QUIC, we would either have 2 round trips with the normal handshake, which is 33% faster, or with 0 RTT, we would get 1 round trip, which is 66% faster. And somehow, they're getting 50. How the hell are they getting 50? That doesn't make sense. Is anybody brave enough to yell out a suggestion on how they might get 50? The average, that is the most common suggestion, also wrong. But it's a good idea. It's a good idea. So basically the idea would be if you have about 50% of the left, 50% of the right, you would kind of end up at 50%. Make sense? However, I'm going to give you a tip. This is something you can use in your career, okay? Always works. Whenever someone who knows anything about networking asks you, what is the problem? The answer is always the same. It's always DNS, okay? Unless it's cache invalidation, unless it's this. But usually it's DNS, right? That was here as well. The problem here is DNS. It turns out that when you do the HTTP2 level setup, you will often incur a DNS lookup as well. So adding more or less 1 round trip, while you didn't have that DNS for HTTP3. But that should also be weird to most of you. Why would HTTP3 not have DNS? It also needs to know where to find the server, right? And this has to do with what I said at the beginning. QUIC runs on top of UDP to make it deployable. However, there are still many networks, many firewalls who, for historical reasons, block UDP. UDP has been used for attacks as well in the past. So especially a lot of corporate networks still block UDP, and by extension QUIC today. Additionally, of course, not the whole internet is QUIC capable yet. So if the browser would just try HTTP3 to every server it sees, and then waits for a timeout on the network to then only switch to HTTP2, that would of course take a long time, typically 30 seconds, and make for a lot of angry users. So the browser, of course, is not going to do that. In fact, the browser today is very, very conservative. It is only going to do HTTP3 if it's sure that server at least can support it. How does it know this? Again, it uses this concept of the bootstrapping connection. The very first time you see a new server, it's not going to use H3, only 1 and 2. The server is then going to send back a new response header called alt-svc, alternative services. The idea being you're currently using the HTTP2 service, but there is also an HTTP3 service at port 443. The browser can now remember this information in its cache, and then after that, if it needs a new connection to that server, it's going to try and open 2 parallel connections. One over TCP and H2, and one over QUIC and H3. Why? Again, the server supports H3, but it might be that the network is blocking it. So if that's the case, the browser automatically falls back to HTTP2, so there's no delay for the end user. If H3 does succeed, it just closes the TCP connection that it doesn't need. Right? So that's how it works in practice. And this now explains what we saw here. When is HTTP2 mostly used? It's for new servers that we haven't seen before. Because if we had seen them, we would have been using H3. So a new server we haven't seen before usually incurs a DNS lookup as well, because it wouldn't have been in our local resolver cache. Well, for H3, we already know this. We have the alt-svc information, probably still in the DNS cache, doesn't incur DNS overhead or less of it. So this is how you get to the 50% faster. Now, I made the argument it's kind of unfair to use DNS in your metric there, right? Because DNS should be something separate. So we worked with Wix to refine their definition of time to first byte, I would say, for this. And then you do get expected results. You can see here clearly that they were not using 0 RTT. They were using the normal QUIC handshake. And that is indeed about 30% faster. Now this is just the time to first byte, the handshake. Of course, performance has many more different metrics. For example, Google now has this thing called Core Web Vitals. One of those vitals is the largest contentful paint. You don't really need to know anything about that. Google says it needs to be lower than 2,500 milliseconds. Well, even in the Netherlands, which is a pretty well-connected country, I would say, right? Even then, just switching to HTTP3 could give you about 500 milliseconds performance benefit on mobile networks. So basically get 1/5 of this Google metric for free just from switching to HTTP3. Which, I don't know about you, I still think that's pretty impressive. Okay? Now the final thing you might be wondering is how, Robin, how can I get my hands on this amazing new technology? Well, the best way today, of course, is to use a CDN. Of course, Akamai is the best, but you also have companies like Cloudflare and Fastly, where it's very simple. You basically just literally flip the switch, you just enable it, and you get the full HTTP3 suite for free. None of these are actually charging extra for all of these benefits. So it's very easy. If you're not on a CDN, you really should be, 1. But 2, if you want to do this yourself, there are options, but it's going to be a lot more work. Okay? There are very stable packages out there, but you really need to know what you're doing to properly set them up, configure them, and secure them, as we just saw. What makes things worse is that most of the popular packages, things like Nginx and Apache, and especially Node.js, do not have support for this yet. In some cases, it's months or even years out. Okay? So deploying this yourself, possible, but know what you're getting yourself into because it's going to be a world of pain. The final thing, do you need to change anything about the front end to make use of this? No, you don't. As long as you already have optimized your pages for HTTP2, they will work perfectly fine on 3 as well. Because as I said, they're basically the same protocol, the same features, just implemented differently. Why am I putting emphasis on this? Because like some of you, I was there 10 years ago when we switched from 1 to 2, and that was a whole lot more work, right? To make sure we were optimized for 2. Now you don't need to do any of that. Finally, to put some of you at ease, do you really need to switch to HTTP3 right now, today? No. Okay? If you can do this easily, please do. If not, you're not lagging too much behind. We currently are at around 30%, depending on how you measure it. But we will still have TCP and HTTP2 for a long time, because QUIC is just very complex. Okay? So it's not like we have to change this now. This is more like making a baseline to be able to evolve the internet for the next 30 years. And if you join now, great. If you join in 5 years, also more than welcome. The main thing to keep in mind is, like with all powerful things, there's always a trade-off between what you get from it and the security aspects that it might entail. So be careful, especially when manually deploying this. And with that, the only thing I can say is good luck and hope to see you next time. Thank you.
All systems are nominal. Initialize Genesis sequence.